Today, we're going to tackle a really crucial concept for anyone building AI, cross-validation. Think of it as the ultimate strategy to make sure our AI is actually learning and not just, memorizing the answers to cheat on its tests. Let's dive in.
So here's the big question, right? We all want to build models that can genuinely think and apply knowledge to new situations. But how can we be sure that's actually what's happening? How do we test for real intelligence versus just a super good memory?
Well, the biggest trap we can fall into has a name: overfitting. And honestly, the best way to wrap your head around it is to imagine a student who's getting ready for a huge exam. But this isn't just any student. This is a student who only memorizes.
Overfitting is when our AI, our student, has memorized every single question from the practice tests. I mean, it knows them perfectly, down to the last comma. But the second you give it a new question, one it's never seen before, it completely falls apart. It didn't actually learn the concepts, it just memorized the examples.
So at the end of the day, here's the bottom line. We don't really care how well the model does on its practice tests. The only thing that matters is how it performs out there in the real world, on totally new data it has never seen before. That is the true measure of success.
Okay, so the most obvious solution to this problem is to give our model a mock exam. But this really simple idea actually creates a pretty tricky dilemma.
The basic approach is just this. You take all the data you have and you split it in two. One pile, the training set, is what the AI gets to study. The other pile, the test set, is locked away in a vault. It's the final exam, and the AI never, ever gets to see the questions ahead of time.
And this image just nails the conflict perfectly. You've got this fixed amount of data, right? It's like a single piece of rope. If you want to give your model more study material, a bigger training set, you have to make the final exam smaller. And if you want to make that final exam more trustworthy, you got to take away some of its study material. It's a constant tug of war. And this really lays out the trade-off. If you make your training set huge, yeah, the model might learn better, but your final test is so small that the score you get isn't very reliable. But if you make the test set huge for a reliable score, your model didn't have enough data to learn properly in the first place. It is a classic catch-22. So how do we escape this dilemma? Well, we get clever. Instead of one single high-stakes final, we give our AI a whole series of mock exams. This, my friends, is the genius idea behind cross-validation.
And this quote really gets to the heart of why we need it. Cross-validation is what you turn to when your data is precious, when you just can't afford to lock away a huge chunk of it for a test you only get to use one time. You need to squeeze value out of every last drop. And that's the real magic trick. It's a system where every single piece of data gets a turn being in the training set, and every single piece of data also gets a turn being in the test set. You really do get the best of both worlds.
Okay, so let's break down how the most common method actually works. It's called K-fold cross-validation. And it starts off super simple. You take your entire dataset and just chop it up into a number of equal sections. We call these folds. Let's say we make 5 of them. All right, here we go. Round 1. You take just one of those folds and you set it aside. That's going to be your test for this round. The model then gets to train on all the other 4 folds all combined together. And this is where it gets really smart. You do that whole process again, but this time you use a different fold as the test set. And you just keep going, rotating which fold is the test set until every single one of the 5 folds has had its turn being the final exam. So at the end of all that, what you're left with is 5 different test scores. You just average them all together and boom, you get a single, much more robust and trustworthy estimate of how good your AI really is. You're not just relying on one lucky test day.
Okay, so cross-validation sounds like the perfect solution, right? But you knew it couldn't be that simple. Like in any good story, there's a plot twist. The results we get from this process aren't always a perfect reflection of reality. We need to talk about bias.
Bias is really just a fancy way of saying your test score might be systematically lying to you. A positive bias means your score is too optimistic. You think your model's an A+ student when it's really more of a B-. Negative bias is the opposite, and of course, what we're always aiming for is an unbiased, accurate score. So why would our test be biased? A lot of the time, it comes down to the kind of data you have. Look at the left. That's intra-subject data. Think of this as having 100 photos of just one person. They're all going to be pretty similar. Now on the right, you have intra-subject data. This is like having one photo each of 100 different people.
Way more variety, right? And here's the problem. If your training fold and your testing fold contain data from the same source, like two brain scans from the same person, they aren't really independent. The test becomes way too easy. It's like the model already saw the answers. And this leads to that overly optimistic score, that positive bias.
So, knowing all these pitfalls, how do we make sure we're doing cross-validation the right way? How do we become wise testers of our own AI?
Okay, first, a slightly technical but really vital point about the math. A common mistake is to just lump all the test results from all the rounds together and then calculate one final score. Don't do that. The correct way is to calculate a performance score for each fold individually, and then you average those final scores together at the very end.
So, what's the final game plan? Here are the big recommendations. First, try to avoid a method called leave one out cross-validation. It can be wildly optimistic, especially if you have that data similarity issue we just talked about. Instead, you want to use methods that ensure your test set is truly separate and independent from your training set. Look, if you take only one thing away from all of this, let it be this. The single most important goal of any testing procedure is to maximize the independence between your training data and your test data. That's it. That is how you get an honest, reliable score. You know, when you really think about it, cross-validation is so much more than just a technique. It's a mindset. It's a philosophy of being skeptical, of testing your own assumptions, and never trusting a result that looks a little too good to be true. And that leaves us with a final thought. What other complex systems in our world, from business strategies to public policy, could really benefit from that same kind of rigorous, honest testing?